Alright, so f of x is just that, right? So we get the quantity x plus 3 to the 3/4. Alright? So what do we do? Okay, so, well, no, derivative, right? We gotta find the second derivative. So, what's first derivative?
X squared, or what, further.
Okay, but we're doing just a regular, you guys are in antiderivative mode, we're just doing regular derivative. 3/4. Okay, bring this guy down.
X to the negative 1/4.
Good. Okay, good. And the second derivative?
Wouldn't we have to use the? Oh yeah, just kidding, come on.
Chain rule, yeah, we do, but the derivative is 1, you're right, yeah. So,
Negative 3/4.
negative 3
16.
16ths.
4 times 4 is 16.
There you go. X plus 3 to the what? Negative 5/4. Okay, good. So let's write that maybe as a fraction. So we end up with negative 3 over 16 times the quantity x plus 3 to the 5/4. Okay, so now we're interested in the absolute value of that, right? So the negative sign, in fact, let's do that. Let's go ahead and do, right, so then we could just get rid of that negative sign, right? Everybody see that? So talk to me about that now. On our interval from 0 to 4, where is this going to have its maximum value and why?
This is 0 because it's inverse.
Okay, it's 0 because, say it again?
It's inverse.
Because the x is on the bottom, right? And when x is 0, that's what's going to make the denominator the smallest, which would make the value of the fraction the biggest, right? Everybody see that? Okay, so we know that it's going to happen at 0. So what is then, what is the absolute value of f double prime of 0? Oh, that's going to be weird, isn't it? Yeah, we're going to get 3 over 16 times 3 to the 5/4, right? Which is going to give us, I mean, we can just leave it like that, that's fine. We're just going to, we don't have to simplify that. We'll put it in our calculator anyway. So, we really could, we have a 3 to the 1 on the top, so what is that? How could I simplify that if I wanted to? What's my rule of exponents say if I divide like bases?
Minus.
Right, I would keep the, so I would subtract 1 from the exponent of 3 top and bottom.
Yeah.
Do you know the rule? This is what I was teaching my algebra 2 guys. When you have like bases, I can't remember if we said this in here or not, I don't know if I probably haven't. A good way to think about this rule, the rule of exponents when you're dividing like bases, is you keep the base where it has the most power and subtract the other exponent. It's a good working algebraic rule. So in this case, 5/4 is bigger than 1. So I keep the 3 on the bottom and subtract the 1 from the 5/4. Just combine some steps. Does that make sense? Okay, so then we could, if we wanted to, write this as 1 over 16 times 3 to the 1/4. Okay, so we'll just leave it. This is going to go there, right? So then now we just need to solve for n. So if we make the substitutions into this expression, what do we get? So b was, what was it again? 4? So 4 minus 0 cubed over 12n squared times that. has to be less than or equal to, what did I say, 4 zeros and a 1? So we could do a little simplifying here, can't we? 4 cubed. What can I cancel on the left side? I could cancel the 16 and a 4 squared, just leave me with a 4 on the top, right? And then I've got 4 over 12. That would just make that a 3. So I end up getting just 3n, so n squared times 3 to the 5/4.
Oh, it has to be 3, 12?
One
What?
Oh, that's
Double check me on this.
Oh, I see.
Is
Yeah.
it to the 1/4 or 5/4?
Well, it's 3 to the 1 times 3 to the 1/4. We might as well just combine those, add the exponents.
Oh.
Okay. So then we get 1 over, what did I say? 3 to the 5/4 times n squared equal, or not equals, is less than or equal to 0.00001. So what do I do to solve for n?
Times it by 3 to the 5/4.
Okay, I can multiply both sides by 3 to the 5/4. Good plan. And then, okay, and then, well, here's where I've gotta flip both sides, Right. which means I flip the sign. Good, so we end up with n squared is greater than or equal to the reciprocal of all that. And then I'll just square root both sides, right? Obviously, we want the positive square root. And let's see what we get for all that work. Okay, so square root of 1, that's gonna be funny, what if I just do 1 divided by square root of all that, so. Okay, does that look good? Good deal. Okay, so this one, it worked.
Yeah.
What's that?
Answer's 160, that would round to 160.
No, because it has to be.
But okay, but you gotta go up. Because remember, maybe that's the issue. Okay, 'cause remember that now this is, what the trapezoidal rule error tells us is that the number of trapezoids has to be greater than or equal to that number. But the number of trapezoids has to be discrete. You can't have a fraction of a trapezoid. And so therefore, 159 wouldn't quite be enough. 160 is a little more than you need, but 159 is not enough, so you always have to push that one up. You know what that function's called, by the way? You know what a function is called if you're always gonna round up to the next highest integer? That's a good one to know about.
There's no end where
It's called the ceiling function.
this is due.
Is it like, the steps?
What's that?
Is it like the steps?
Yeah, it is. It's, whereas just a rounding function, when you round, you always round. You know the rules for rounding decimals. But a ceiling function, like for example, the ceiling of 1.51 is 2.
Okay.
What do you suppose the function is called where you always round down? Floor. It is. It's called a floor function. Yeah. All right. So what I want to just, I realize you guys need to finish some things up. So what I'm going to do, at least for a while here, and as long as we need, I'll go ahead and I'll give you a 3-to-2 ratio on lab days here for a while to class days. So we'll just plan on going like Monday, Wednesday, Friday, lab, and then we'll just do, we'll take care of some of this kind of stuff in class. Any other issues on or is it just a matter of kind of finishing things up? Okay. All right. I know what I was going to say. On this last problem, being as you have your graphing calculators anyway, these are all pretty easy second derivatives to analyze, but here's our second derivative function right here, and there's the absolute value of the second derivative function. What if you got one that was a little bit harder to analyze? And you're not going to on the test, but what if, being as you're doing the trapezoidal rule on a calculator anyway, what would be an easy way to analyze where this function had a maximum value on its domain using a calculator? Remember, that's what we're trying to do. We want to find where in the error approximate, or the error formula here for trapezoidal rule, we just want to know where this thing has its maximum value and then get a value for that. Yeah, why not? Sure, you could just graph it, couldn't you? Right, we could just take this function right here and graph it, go up to y1, and actually graph the absolute value while you're at it, right? So remember where that is? Math, number 1. How about that? I'm going to be fancy and use my fraction template.
Ooh, check you out.
Yeah, I know it. I
I
know it.
always use those just because it makes it easier.
It does. Yeah, it's
Looks better too.
Yeah.
16. What's that? 3 to the. Oh, I'll use it again. Not often you get a chance to do that twice in one problem. Okay, and then what do I do from set my window from 0 to 4? And then we'll just go zoom 0. Oh, how about that? What'd I do? Oh, I can't actually. No. Oh, it's plus 3. I put times 3. So it would. Oh, yeah. Whoops. Yeah, you're right. You're right. Nice. I'm going to blame that on the cold medicine. Yeah, I needed an X plus, didn't I? Now, why is it doing that, though? Huh. Now I think it'll. There we go. How's that?
That'll work.
No, you need 3 on the top and it's 5 plus.
Oh, yeah. Well, that's the same thing. Same thing, though, as 3 to the 1/4. Oh, no, it's not. Never mind. Huh. Jeez. At some point, I'm going to have to stop blaming this on cough medicine, aren't I?
Yeah, 2 to 3. See, Trace.
What?
What is it? Trace.
All right, there we go. Does that look good?
Yeah.
I think that's okay, isn't it? Okay, looks good. So now we'll go zoom 0. Okay, so sure enough, we get our maximum at 0. And then if I wanted to, I could even just go trace 0. Remember that shortcut? And it gives us, and hit enter, and it gives us the exact value at 0. And so if I just take that out to a bunch of places like that, that's going to be good enough. I mean, we're going to, we're only calculating the trapezoidal rule out to 5 places. So if I took that out to 7 or 8 or 9 places, it's going to be adequate. Okay. All right. Okay, what I wanted to take a quick look at today, I want to fill a hole.
It's not so. It's quiet.
I know, I can't see.
I want to fill a hole in the power rule. Okay, you guys know what to do for the power rule for antiderivatives. Like if I give you something like this. What's the antiderivative of that?
1 over n times x to the
N
1
plus
plus
1.
Okay, so say it again. X to the n plus 1. Another way of saying it would be divided by n plus 1 plus c. So if we threw a few numbers out there, let's just kind of, like we could, for example, what if we did the antiderivative of x squared, right? We're going to get what? X cubed over 3 plus c. If we do the antiderivative of x to the 1, we get x squared over 2 plus c, right? In fact, this even works for x to the 0, doesn't it? Oops, I forgot my dx's in there, didn't I? There we go. What's the antiderivative of x to the 0?
1.
Yeah, so it really works. Now we wouldn't necessarily apply this rule. I mean, we just know the antiderivative of x to the 0 is 1, right? Antiderivative of 1 dx would just be x, but technically it works. I get x to the 1 over 1 plus c, right? What if we try some negative values? What's the antiderivative of x to the minus 2? Okay, so, or in other words, x to the negative 1. I just want to show you that it does work, right? Okay, those all work. Okay, but why am I doing this? I mean, you obviously know how to use the power rule, but what about this? What's the problem with that? If I try to apply the power rule, what happens? I'm going to get x to the 0, which is 1, divided by 0, which is nonsense, right? You can't do that. Okay, so the power rule doesn't hold for this one value. Now, the power rule holds for, it's not just for integers, as you know, it works for fractions, it works for irrational numbers. So we could do this, we could take the antiderivative of x to the negative 1.000000001, and it would work. We could take, x to the negative 0.9999999, and it would work. But it doesn't work for x to the negative 1. Okay, so how do we fill that gap? It seems like it's just a minor little flaw. But it turns out that this opens the door for some great physics. The behavior of what we need to fill in this gap in the power rule is arguably, I can't say it's the most important, but it's a really important function. It shows up in the natural world as much as anything, if not more than anything else. So what is it? Okay, here it is. Well, the definition of what fits this rule, the power rule, comes from this other function that you used a little bit last year, maybe the year before too. Okay, what's that look like? We call this, by the way, the natural logarithmic function.
What is that thing under the one?
It's a t. So it's our dummy variable.
Yeah, I didn't know if it was a special rule.
No, it's just
to see,
it's-
we're throwing in new stuff, not just
I know.
what else,
I see.
There we go. Okay, so the natural logarithmic function then is defined as this area function using calculus. So what does that area function mean? This is like the stuff, now this harkens back to the second fundamental rule of calculus, right, where we looked at area functions a little bit, the behavior of area functions. Here's the first chance where we get to really actually see one that's important, okay? So what's that mean? What's that t mean again? You remember? It's the natural log of x, so x is the independent variable of the log function. What's this t doing? T for Tony. That's our what we call our dummy variable. That t, all that's really there to do, remember, is just to define the shape of the 1 over t graph. Okay? So what does that graph look like? What does an inverse graph look like? As x approaches, or as t approaches 0 from the right, what value does 1 over t approach? So if we get small positive values on the bottom. Infinity, positive infinity, right? As t approaches positive infinity, we get very, very large positive numbers in the denominator. What value does 1 over t approach?
Negative infinity.
0.
0.
You're infinity off.
And so it looks
I
like,
can't really say that you're close.
it looks like that. Okay, that's the graph of an inverse function, at least for the positive values of the domain, right? So this area function, what's this area function? The area function is just adding up, the natural log of x is defined as the area under this curve, added up from 1 to x. So if this is 1, and this is x, then this area right here is defined as log x. Okay. About that. Okay. So let's use that area function to try to come up with a sketch of what the graph of a log function would look like in a Cartesian plane. Okay, so what if we're going to do something like this? Let's graph this log function. What are some values of the log function that you would know? What's going to be the natural log of 1?
1. 0?
How come?
0?
You're right. How come?
Hold that on my butt.
How'd you get the answer? You must have seen something.
No, I didn't see anything, I just remembered it.
Oh.
I
Oh,
just-
okay.
Sorry.
So it is 0, but why is it 0?
Explain that.
Now, someone's got to explain this to me. How come? What's the area
I can't get my
under
word out.
this graph, this 1 over t graph,
Coriolis.
added up from 1 to 1? Right? You guys getting this back there?
Oh, yeah.
Okay, so that area would have a width of 0, right? So the area's gotta be 0. So there's one point that we know. We know that the natural log of of 1, sorry.
Sorry I couldn't explain it for you.
That's all right. The natural log of 1 is 0, so there's a point on our graph, right there. Oops. Okay, now what's happening, just qualitatively, what's happening to the value of the function as x increases? As x increases from 1 up to like 0.1 to
Y
0.2 to
decreases.
0.3.
Why it's lower?
Well, okay, now y is the area under the curve. So it's the accumulated area. Is this red area that we're adding up from 1 to x positive or negative? It's
Positive.
positive, isn't it? Okay, what's happening to the rate at which we're accumulating area though, as x increases?
Slowing down.
Low.
It's slowing down, isn't it? Right? Once we get pretty far out this function, and the function starts to hug the x-axis asymptotically, then as we move along in the positive x direction, we're adding eventually very, very little area, right? What's that gonna do to the shape of the curve? As x increases, the value of the log x function is increasing, but at a slower and slower rate. So if I had to kind of sketch the profile of this log function going this direction, what would it be? Let's just say it starts off increasing at like that rate. Is the slope, okay, the slope's gonna have to decrease, isn't it?
Yeah.
Right? Something like that. Does that make sense? Okay. What's gonna happen to the left? If we move back to the left, let's add this area up in blue, just to distinguish. What if we went back to, for example, 0.5? That's gonna be the area. What's the sign of that area gonna be? If we're going from 0 to 0.5?
Negative.
Negative and what? You're right. How come?
Oh, because we're going backwards.
Because we're going backwards. Yeah, if we add the area up in this direction, from right to left, that makes it negative, right? And so we get some negative area. Now, what's gonna happen to the rate at which we accumulate area as we get closer and closer to x equals 0?
Speed up.
It's gonna go up and up and up because this thing goes up forever, right?
Yeah.
You see that? So it's gonna get bigger in a negative direction. And so the curve down here is gonna look like that, right? Okay, could we ever get to x equals 0?
Probably not.
No,
We can't, for a couple reasons.
but we can't.
Give me one reason why this function would be undefined at 0. It's gotta be asymptotic at 0. What's one reason why that's the case? What do you think? Let me throw something out here. How come the log function is undefined based on this definition? Why? Can't divide by 0, can we? Right? So if the natural log function being just defined as this area function, if we try to evaluate this from 0 down, or 1 down to 0, at 0, look what's gonna happen, right? We got this 1 over t in here, it's not gonna work, is it? Right? We can't divide by 0. So because of the nature of the natural log function being related to this inverse function, it's undefined at 0, okay? So this is the domain of a natural log function. The domain is it's only gonna be defined for positive values of x. It's got this distinctive shape to it, okay? There are some properties of logs you might remember. What happens if you try to do, okay, what is any kind of log, but natural log is fine. What is the natural log of a product? Not a selling product. Of A times B. Do you remember? In pre-calc and owner's algebra 2? Think about what a natural log function does. It simplifies things. natural log functions are useful to us in calculus because one thing they do is they make arithmetic operations easier. So it ratchets a product down to a sum. If you kind of think of the hierarchy of complexity of arithmetic functions, at the very lowest level, you've got adding and subtracting. Above that would be multiplying and dividing, right? And above that would be exponentiation. Logarithmic functions, the properties of logs, just move everything down the ladder one rung. So this becomes log of A plus log of B. Okay, remember that stuff? Okay, by the same token, what's the natural log of A divided by B? Good, natural log of A minus
B.
natural log of B. Very good. Okay, what about the natural log of A to the n? So that should move it down from exponentiation down to multiplication of
Natural log
division.
of A
Good.
times N.
Good.
Yes.
Same thing, just for
Oh.
commuting. Yeah. Okay, good. Now,
Wait, why isn't it like log of 8 times log? Why isn't it log of 8?
just isn't. Just isn't, yeah. There are some ways we can kind of justify that, but at this stage right here, just take this to be kind of a reminder of those rules. Okay. There's some ways we can justify that pretty easily by, I'll do a little of it today. That's a whole ball of wax. So what about this other possibility then? What if we have the natural log of A plus B? Can that be simplified? A plus B or A minus B? We can't do anything because we've already gotten to the lowest rung, right? Think of it, if you think about the lowest rung on the ladder being addition and subtraction, there's no place to move down anymore, right? And so this doesn't simplify. You can't do anything with it, it's just that. You're kind of stuck with that logarithmic expression. Okay, so a couple other more other little review items. So really a natural log of x, and this is, hopefully this is ringing a little bit of a bell. This is same thing as a base E log. Remember talking about bases of logs? Okay. If you have a base A log,
Yeah, because there's a lot of rules that logs.
yeah, lots of rules. What's the equivalent exponential statement that we can make? Do you remember how this works? Whenever you have a logarithmic equation, you can always trade that for an exponential equivalent. Remember how that works?
It would be A to the 2, A to the.
A to the y.
Yeah.
A to the y equals x. Good. Okay. All right. So now this is, I'm jumping ahead a little bit. This doesn't even come up in the calculus book yet, but this is good to know. There's a rule. The way I always, I mean, after you do this for a while, you just kind of remember it. But the way I initially remembered this, at least, was I always remembered the statement: a log is an exponent. So the log itself has to be equal to what eventually becomes the exponent. Okay, it also makes sense from the standpoint that this is what we call the base of the logarithm. But what's the base of an exponential function? That, isn't it? Right? So the base has to be the same in both parts, right? And that's really the only way it could work then. Okay, so it seems to me like we ought to be a little out of shape with this, but if we were to do something like this rule, we ought to be able to figure out pretty easily, make sense of it by looking at it this way, I bet. So if this is a base E, right, then that'd be the same thing as saying, if this is like our Y, right? This is the same thing as saying e to the n log a equals a to the n. And how's that work? That's supposed to be an e. Whoops. And natural log of b is 1. I guess that's not a great way to do it. We shouldn't use natural log there. Yeah, because it would have worked with the base a. Log base a. Nah, it's not going to be easy to see that way. Never mind. Never mind. I've gone off on a tangent. Okay, so we've got these properties of logs. Oh, what's the log of e then? So if we go back to our graph here, what do you suppose the natural log of e is going to be? We can look at this a bunch of different ways. So the natural log of e would be the area under the curve from 1 up to e, right? And if we use our properties of logs, let's see. We could say that the base e log of e, if that's equal to y, that's the same thing as saying e to the y equals e, right? Does that make sense what I just said there?
Yeah.
Using this relationship right here,
Oh, yeah.
right? If this becomes an e, and that becomes an e, right? Because if we're taking the natural log of e is the same as the base e log of e, right? Isn't that the same thing as saying e to the y equals e? So what's y? If e to the y, yeah, it's 1, isn't it?
1.
It's 1 because there's a 1 there.
72.
Does that make sense? Okay. So we know that if the bases are equal, the exponents have to be equal if the powers are equal, right? So there's another rule that we have. We know that the natural log of e is equal to 1. And we'll use these. I'm going to give you guys a little assignment. I can tell you could use a little refresher on this. I'm going to give you a short little assignment, just kind of practice your properties of logs a little bit. But see if we can fill in the blank. See if we can do this. Okay, so what we're really building towards here is just that answer. I want you guys to be able to do, use log functions algebraically, but do some calculus with them. What do you suppose the derivative of natural log x is? Oh.
E.
No. To be continued.